Assalamu alaikum. Welcome to lecture 25 of data mining. We are nearing the end of this semester, so we have a couple of lectures left after this. So we have completed major topics in this course, and we now have some assorted topics that we'll be discussing. So I talked about a few topics in the previous lecture. We talked about some additional classification techniques, the k-means classifier, the k nearest neighbor classifier, and then we also talked about the Bayes classifier in general. And we also talked about a new clustering similarity, new way of computing the similarity between two objects. And the technique called the shared nearest neighbor approach is quite effective for high dimensional data sets. So today we will be talking about some concepts in graph mining. We will be introducing the idea of a graph and their properties, and then we will discuss some additional measures, you can say, or stats by which you can quantify the various aspects of the graph, like the nodes or the vertices in the graph. So following this, we will be defining some ways of quantifying similarity between nodes in a graph. We will also then talk about briefly about the page rank algorithm, which follows from this. And we will also discuss some very simple techniques for finding communities in social networks, which are basically also graphs. So that's the idea for today. So let's get started. Are there any questions? So as I said, we'll be talking about graph mining and some concepts related from graph. Uh, so first of all, what exactly is a graph? So graph, as you already know, is a connected uh, structure which consists of vertices and edges. So in general, mathematically, we can define a graph G as two things, combination of two things, vertices and edges. So vertices, basically we are vertices, or sometimes we also call them nodes. So these represent various entities of interest in our analysis. And E basically are edges. We can also call them links. So these basically represent the relationships between the nodes or entities in our graph. Okay? So basically, the number of vertices is often the size of the graph. Is a measure of the size of a graph. We can denote this by n. Okay? So n is the number of vertices in the graph. And the edges, so each vertex, let's say we define a vertex simply by the index I, for example, you can define the vertex vi as well. So vi would be a vertex in the or node in the set of possible vertices in the graph. So as I said, I can simplify this by simply using the index I or the single character I to denote one node in V. So ij are essentially nodes in the graph. Okay? So I is equal to 1 to n. And an edge is a pair of nodes. So I, j is a pair. So this would be in our set of possible edges. So if this pair I and j exist in E, then we say that there is an edge between I and j. And if we do not distinguish between the order, for example, if j, so if we do not distinguish between the order of these nodes in the pair, then we say that this is the indirect graph or undirected graph. So indirect graph, uh, so basically in that case, we simply have an edge between two nodes and no direction between them. While on the other hand, we have what is known as a direct graph, in which case uh, ij would be different from ji. So ji means that there is a link from j to I, and ij means that there's a link from I to j. So there's an arrow from I to j or an arrow from j to I. So if this is the case, then this would be a direct graph or a directed graph. ठीक है? So if you don't have both of these combination, then it is an indirect graph or an undirected graph. So each node can also be assigned a label. So label for nodes. So this label could be anything. So it could simply be a letter, for example, a letter A, B, C, for example, or it could be something else. You can define more descriptive labels like let's say if each node is representing a person, you can write the name of that person. So for example, Atif, Asim, and so on. So you can assign a label to it. And also sometimes if your graph is quite more descriptive, you can assign features for each node. So each node may be represented by a feature vector. So depending on the entity that's represented by a node, for example, a node may be represented by a document, for example. So you can have a full representation for the document as a vector for that node. Okay, so that is also possible. So as I said, a node is identified by index like I, J, K. A node can also have a label, which is a descriptive label that reflects the type of data that you're modeling in your analysis. And then you can have even more description for that node by capturing the features of that node in maybe a feature vector. Uh, Now moving on to the edges. So we said that edge is a link between two nodes. It could be directed, it could be undirected. Uh, and each edge can have a weight or some other additional information. So you can have a weight for edges. Okay. So usually you can denote a weight by W subscript I and J. So this represents the weight associated with the link from I to J. So if it's undirected, so Wij and Wji would be the same. But if it's directed, this may be different. This can be different. Okay, so you can have a weight associated with the link. So weight is usually a scalar. So this is a scalar and usually it's numeric. Okay? But again, in general, you can have features associated with an edge. So this again can be a feature vector. Okay? If you want more description to be associated with the edge, you can have a feature vector describing it. So this information that I've just discussed is defining the structure of a graph. As I said, a graph can also be called a network. The vertices are connected by edges, and vertices may have labels, they may have features. Edges may have weights or they may have features as well. And the graph can be directed or undirected. So before moving on, let me just mention some example domains in which graph arises. So, and many of these examples you already know. Uh, so graphs arises naturally in many domains. Uh, so one of the common domains is social networks, and the name itself has the name networks associated with it, so it means it's a graph, social networks. In this case, nodes are basically actors. Actors means that there is some human that is associated with a particular node. So, for example, if you think of Facebook as a social network, so each Facebook ID has a human associated with it, and that human may then be related to other humans through this graph, through the friendship network. So, the edges in the graph or network would represent relationships. So relationships can also be called ties in the context of social networks. So the ties could be friendship ties or in general some relationship you are communicating with that other actor or not. Okay, so nodes are actors which are entities controlled by humans, and then edges are in general relationships, and they can represent various forms of interactions between those actors. So that is the social network. Of course, social networks are quite common nowadays. So Twitter, Facebook, whatever, email networks, even phone networks. All of those are examples of social networks. Then computer networks. Again, these are graphs. So nodes or edges are computers slash servers slash you can say devices, IoT devices, and edges are basically communication links. Okay, so those computers can communicate through those links, so they are connected. So the World Wide Web is a computer network. You have servers that have pages on them, and you have clients that connect to them and retrieve pages from them. And then you have networks arising in many other domains as well. I'm not an expert in them, but for example, chemical structures, for example, are graphical. So nodes could be atoms slash ions, and the edges could be uh, bondings or types of bonds between those edges. And these structures contain important information regarding the properties of those compounds that they represent. So that's why uh, chemistry people tend to study this in great detail, the structures of compounds. And you can also have networks arising in bioinformatics. So you can have structures, protein networks, for example, could be structures. You can also have relationships. So, for example, protein networks and so on. Even if you think of biology and the broader aspect of biology, you can even think of ecology as forming social networks. You have various animals living in an environment and they are interacting with one another in some way. And of course, you have lots of examples here. Uh, and of course, in computer science itself, you have examples. For example, you can think of document networks, for example. So you have documents that are linked together based on whether they are the same topic or not, or whether they use similar words or not. Uh, Coming back to our basic graph and network. So we talked about nodes or vertices. So nodes and vertices can be of the same type or in a particular graph, or they may be of different types. So the types of nodes. So generally they will be same, in which case uh, we have a regular graph. Okay. But if you have, let's say, two types, so we can have what is uh, so again, you'll have to identify those types. So if you have two types, then you have a special type of two types, which is called a bipartite graph, in which, uh, for example, an example of two types would be, let's say, you have nodes that are documents and words. So two types of nodes. One node is a document, another node is a word. And in this particular case, so let's say on the left, I'm drawing nodes that are documents. So let me just to distinguish them, let them call them squares. These squares. And on the right, I have words. I draw them as circles. So if a particular document has a particular word in them, you will have an edge between them. Okay? So in this graph, there are no edges between nodes of the same type. So for example, there are no edges between words and there are no edges between documents. There are only edges between words and between words and documents. So this is an example of a bipartite, as I said, bipartite graph. So there are two different types of nodes, and the edges only pass between those types. Okay. And of course, you can have multiple types of nodes in a graph, and the connectivity usually would uh, be of different types between the types and within the types of nodes. So in the case of bipartite, as I said, there are no edges between the nodes of the same type. This would be a bipartite graph. Okay. Uh, okay. Now coming to some properties, general properties of the graph before we move on to studying some more specific properties. Uh, so we have what is known as, so first of all, n is the number of nodes in the graph. Okay. Uh, the maximum possible number of edges in the graph, if the graph, let's say, is undirected, would be what? Basically fully, what we call as a complete graph. So if a graph is fully connected to nodes, and then we have basically n into n minus 1 over 2 edges. So this is for indirect, fully connected graph. So such graphs are also called complete. So if there are edges between every pair of nodes in the graph, then we call it a complete graph. ठीक है? So basically, n nodes हैं, तो possible number of indirect edges would be n into n minus 1 over 2. And if you have a directed graph, it will be n into n minus 1. Divided by 2 खत्म हो जाएगा. ठीक है? And in general, it will be actually n square. Okay. Okay. So, okay, that's the size of the graph in terms of the nodes and the edges. As you can see, the edges, the number of edges is usually a power of the number of nodes. So you usually have more edges than the number of nodes. Of course, if it is a sparse graph, it may be less, but in most practical cases, you have more edges in general than the number of nodes. Okay. So we have another concept called degree of a node, and we can denote this as di. So degree of a node is basically the number of uh, edges that are incident at that node. Of course, then you have to make the distinction. If it is an indirect graph, you just simply count the number of edges. If it is a directed graph, then you have two cases: the number of edges that go away from the node and the number of edges that come to the node. So you'll have two Ds, one for the outlinks and one for the inlinks. So degree is basically, so if you have an indirect graph, which is basically not directed, so maximum possible degree of a node would be n minus 1. बस एक नोड ith हम नोड कंसिडर कर रहे हैं, there will be n minus 1 other nodes. उनके साथ वो connected है, तो इसकी डिग्री n minus 1 हो जाएगी. The maximum possible value would be n minus 1. So similarly for directed graph, maximum possible value would be n minus 1. But as I said, for directed graph, you will distinguish between inlinks and outlinks. So min, of course, basically the range here is 0 and basically n minus 1. So if a node does not have an edge, it means that it is not connected. ठीक है ना? It is not connected, and oftentimes we will call it a disconnected. It's not a connected component. Okay, if it doesn't have any edge with any other node in the graph, so it's not connected to the rest of the graph. So usually in practice, we will consider that to be separate from the rest of the graph. But from a purely theoretical perspective, it's not connected to the graph. ठीक है, so ये degree हो गया. Some other concepts, any portion of a graph is called a subgraph. Okay, so this subgraph would contain a portion of the graph with its nodes and its corresponding edges. Okay, and a subgraph that is fully connected is called a clique. Okay, so for example, if you have a graph and all you have nodes from each node to every other node that's fully connected, we call that a complete graph as well. ठीक है ना? But if you talk about a sub part of a graph, उसको हम and is fully connected, we typically call it a clique. Okay, so fully connected portions of a graph are of interest in many applications. So in the case of social networks, they may represent a group of people that are forming a community. They communicate with each other frequently. Okay, so they're connected to everyone else in that community. So community discovery थोड़ा सा हम बाद में देखेंगे भी next lecture में. ठीक है. ठीक है. So I think we have covered most of the terminologies and concepts. So let's move on. Mm. Of course, graph theory is a deep topic, a topic that is studied by computer scientists as well as mathematicians, and there is a lot of theory associated with it. Uh, so okay. So now let's move on. So we have defined a graph, we have defined some notations and some properties. So now let's look at some very simple ways of quantifying the importance of nodes in a graph. So remember, a graph is a connected structure, nodes and edges. A node in a particular graph is connected to other nodes. So based on that connectivity, we will like to kind of quantify the importance of that node. So maybe it's a social network, a node would be an actor. So how important is that actor in the social network? Okay? And of course, it could be a computer network. Connectivity and importance of a node may be also be important in terms of, let's say, security or virus immunization and so on. So there could be numerous applications. Okay? So there are two broad concepts for importance. One is called centrality, and the other is called prestige. Okay? So these are two broad concepts for quantifying the importance of a node. So let's start with centrality. So centrality basically quantifies how central a node is in the graph as a way of quantifying its measure. It uses the notion of centerness of a node in a graph as its measure of importance. Okay? So if a node is smack in between in the center of a graph, then it should be of greater importance and centrality should be higher. So that's the main idea. So if we talk about a social network, Uh, so a person that is in the middle of a community who communicates with everyone else in the community would be an important person. Usually the notion of centrality applies to indirect graphs, and direct graph by considering only outlinks. So this notion of centrality does not consider inlinks. If you talk about a particular node, उससे जो बाहर जा लिंक्स जा रहे हैं उसी को हम कंसिडर करते हैं, इन लिंक्स को नहीं कंसिडर करते. ठीक है. So इसमें आप तीन नोशंस हैं. Let's go over them one by one. The first notion is basically degree centrality, the simplest way of quantifying centrality. So, so the degree centrality, let's say C D of a node I is simply DI. Of course, if you want to normalize this, you normalize it with what? Maximum possible degree of a node, which is what? N minus 1, right? So if a node is connected to every other node in the network, di would be n minus 1, numerator भी n minus 1 होगा और denominator भी n minus 1 होगा, and we have a maximum value of 1. And of course, minimum value would be 0, which means that the node is not connected to the graph, to the rest of the graph. Okay? So why is this n minus 1? Because total number of nodes graph में n है, तो हम ith node consider कर रहे हैं, तो बाकी remaining nodes are n minus 1. So आपके पास जो degree है, it can maximally be n minus 1. So we are not considering the degree if there's a loop back to the same node, वो नहीं consider करते typically. ठीक है, so this is a simple way of quantifying the importance uh, of a node. The other notion is that of closeness. So this notion also considers how far away a particular node is from the other nodes to which it is connected. Okay. So previous one was just looking at connectivity. Now it's looking at, by the way, the previous case we are looking at direct connectivity. Degree is direct connectivity, connected to directly. While in this case, closeness, uh, they may be, I and J may be connected, but they may be connected through multiple links. But since multiple links है तो उसकी closeness कम होगी, तो इसको quantify किया हुआ है. So the distance between I and J, so this is the distance between two nodes I and J in the graph, and it could be the weighted distance, but here we are just uh, saying the number of edges in path, usually the shortest path, if there are multiple paths between I and J. So if there are multiple paths between I and J, we'll be considering the shortest path, and we say that this is Dij. Okay? So, for example, आपके पास uh, if there are two links between two nodes, so let's say मेरे पास एक node, let's say one है node, and then you have the edge here, you have node 2, you have an edge here, node 3, you have an edge here, then you have node 4. So the distance between 1 and 4 would be equal to 3 because 3 edges. Okay? So we are considering each edge to have unit weight. Weighted भी आप कर सकते हैं, but here we are just considering simpler case. ठीक है? So if this is the case, then how do you define closeness centrality of a node I? So normalization इसकी actually ऊपर आती है n-1. पहले मैं लिख लेता हूँ, I'll explain this later. Divided by, we have a summation uh, for all j in the graph of d, I and j. ठीक है? What is dij in the denominator? So j is any, of course, so j is not equal to I. So okay. So of course we are not considering that particular node as well. So नीचे denominator में sum है. So if I is connected to some nodes j, so we'll sum their distances. ठीक है? और वो denominator में आ जाएगा. So what are the cases here? So of course in this, so let's say if I is connected to every other node directly, डिग्री उसकी n-1 है, और वी आर टॉकिंग अबाउट इनडायरेक्ट ग्राफ, तो ऊपर न्यूमरेटर में भी n-1 हो जाएगा और डिनोमिनेटर में भी n-1 हो जाएगा. दिस विल गिव यू ऑफ कोर्स 1. बट लेट्स से इफ दे आर नॉट कनेक्टेड डायरेक्टली, n-1 ऊपर तो कांस्टेंट है, नीचे द डिस्टेंस वुड increase beyond n-1. So it will, and this value would become less than 1. Okay. So if I take an example, let's say, so n let's say is, let's say 10, ऊपर मेरे पास 9 होगा और नीचे 9 होगा. This will be the case when it is fully connected, directly connected. The other case would be 9 divided by, let's say, नीचे 15 हो गया. So this would be a smaller value. So if I has a direct link with every other node, it has the highest centrality of 1. If it is connected with other nodes through intermediate nodes, then its centrality would be less. So note that this measure is not defined for a disconnected node, because denominator में फिर 0 हो जाएगा. तो denominator में 0 हो जाएगा, तो this would not be defined. So there are no nodes that are connected to I. The distance of I to j would be undefined. ठीक है? So this is a more expressive measure of uh, importance and centrality. So moving in the same fashion, we have another centrality which we call betweenness centrality. ठीक है? So closeness looked at how far a particular node was from other nodes to which it can be reached, to which it can reach. And betweenness is looking at whether that node lies in the path of many other nodes. ठीक है? So इसका जो social network का concept ये है कि if you have a very important person, so everyone would talk to that person. ठीक है? So he is between, it's kind of a coordinator type of person. So that person would be important. Okay. If many people uh, can, so in other words, so if you want to talk, so if you have a graph, okay. So we are talking about a particular node I. So for example, let's take node J and K, some two node J and K, which is not I. If there are many such pairs of nodes J and K for which I lies between their path, then it means that I is important. Okay? So if there are many paths between other nodes in the graph J and K that has to pass through I, then it means that I is important. So if I does not lie on the path of other nodes, then I is less important. So this is the idea, and we'll need to quantify this. Okay. इसकी quantification, let's define P. Jk is the number of paths from J to K that pass through I. Remember, there could be multiple paths and there could be multiple shortest paths. मतलब let's say shortest path का distance 3 है, तो maybe 2-3 के paths I से गुजर रहे हैं, तो ये वो number है P J K. ठीक है? And then we will also need the distance. We have already defined the distance Dij as the distance from just trying to figure out कि formula थोड़ा सा ज़हन से निकल गया. Okay. So betweenness centrality of I equal to So we will have so P is the number of paths, okay, and then we have to divide it by the distance, okay. So P JK divided by sum sum of the distance to J to I. So there has to be number of paths that pass through I. Sure. I think it doesn't do the distance. Okay. So what is the total number of paths between any pairs of nodes that does not include I? So that would be, if this is an indirect graph, it would be n minus 1 into n minus 2 divided by 2. ठीक है? So indirect graph, हमने दो नोड्स निकाल लिए ग्राफ में से, J और K निकाले हैं. ठीक है? So this is going to be used for normalization. So this is total number of paths और जो actual paths हैं वो P J के हैं. तो हमारे पास फिर जो बन गया definition B P J K divided by the normalization, which is basically n minus 1, n minus 2, and then 2 ऊपर आ जाएगा आपका. So this is basically the formula for the betweenness centrality. So of course, if there are no paths that goes through I, तो ऊपर जो Pij है वो 0 होगा. So this will become 0. So if all n minus 1 multiplied by n minus 2 over 2 paths go through Pj के, तो Pj का नंबर भी वही होगा, तो ये 1 हो जाएगा. So this is the betweenness centrality, which kind of quantifies the number of paths in which this node I lies in the graph. So all of these जो मैंने ऊपर equations लिखी हैं तीनों की, they can be applied to directed graphs as well, only that you would then be considering paths that are directed paths. Okay? And also, as I mentioned before, centrality of a node is generally considered by the outlinks. For degree centrality outlinks पे सिर्फ depend करती है, not inlinks. And for the other two cases वो paths हैं. तो paths ordered path होना चाहिए, arrow वाले path हैं. So the other concept, let's move on to the other concept, which is called prestige. तो prestige के भी इस तरह दो तीन further ideas हैं. The simplest case is of course degree prestige. ठीक है, तो C centrality PD कर देते हैं इसको of I is simply DI divided by n minus 1. तो ये फॉर्मूला ऑफ कोर्स वही है जो पहले था, but as I mentioned earlier, prestige considers in links only. So let me first define prestige. So prestige basically works for directed graphs and considers in links for degree. Okay. So what is the idea of prestige? So the idea of prestige is if many, again, let's give the example of social network where the node is an actor. If many people refer to a person, meaning that you have an in link, so that person would be more important. Okay? So that's why a degree prestige looks at in links. So more prestigious person. So for example, a department's chairman or chairperson is a more prestigious person than, let's say, a regular faculty member, because all faculty members would refer to the department chairperson. Okay. Mm. Okay. So of course, degree prestige can also have a maximum value of 1 and minimum value of 0, which means that the graph is not connected or the node is not connected. Uh, इसमें जो दूसरी prestige है, which is very similar to closeness, centrality, here we call it proximity prestige. So proximity prestige basically looks at the influence uh, network of a particular node. So, so if you are talking about a particular node I, we are considering the set of nodes capital I. So capital I sub I. This is the set of nodes that can reach I. Remember index की बात हो रही है, directed graph है, ठीक है? So capital I sub I is a set of nodes that can link to I, meaning that they can approach I. So the larger this number would be, the more prestigious that person would be or that node would be in the graph. So we would like to quantify this idea. Okay, let me just think out किसका formula क्या है. And of course, a set of nodes that can reach I, you also have to consider their distances. So proximity prestige also considers their distances. Okay. So so basically Ji. So this is the distance from J to I. Remember, this is directed distance now. We are coming from J to I. Okay. So what is the average distance of all nodes to I that are linked to I? We can simply calculate that average distance as, of course, the set size I sub I divided by sum of all nodes j, that is not, of course, I, of d, j and I. ठीक है? तो ऊपर fixed number है, so this is the set of people that can reach I. This maximally could be n minus 1, right? All nodes can reach I, and if they reach by one hop, then this ratio would be 1. But if they reach by longer hops, then this ratio would be less than 1. Okay, so this essentially is your uh, just a second. This is for all nodes j. Sum हो गया इसका. By the way, the distance d is again edge distance. We are assuming the weights would have a distance of 1. Edges would have a uh, edges would have a weight of 1. So ऊपर आपके पास maximum, ठीक है, and n minus 1 possibility. If it is less, then of course the denominator will be less होगा, ज़्यादा है तो less है. ठीक है. So this is our proximity prestige. The prestige P of I. ठीक है. The maximum value of 1 and minimum value of 0. If the set I is 0, of course this can is defined for uh, disconnected nodes as well. Remember जो closeness centrality हमने define की थी disconnected nodes के लिए, वो undefined हो जाता था, D नीचे आ रहा था. तो यहाँ ऊपर 0 हो जाएगा, तो then that should be fine. ठीक है. So the last prestige one is called rank prestige. So the idea in rank prestige is the prestige of a particular node, a particular actor would depend on the inlinks, of course, as we have seen before, degree prestige as well as proximity prestige, but also on the prestige of those nodes that are linking into it, that person. Kind of recursive definition है. ठीक है. So again, to explain this, so let's say, uh, so give an example of myself. So for example, I am asking I am basically referred to by mostly students. So those students may be plenty, right? They may be, let's say 20, 30, 40, those who take a class, those who are working in my lab. These students refer to me or in link to me. So this, but each of those students may not be of, would not have very high individual prestiges. So this means that the prestige of Asim would also be not as high. So let's just take another example. So let's say we have an actor called VC. VC would be referred to by a lot of people who are at high administration positions. So department chairs, for example, deans, directors, and so on. So each of those link directly to the VC or connect directly to the VC, and each of those also have a higher prestige. So this would mean that VC would have a much higher prestige as compared to, for example, Asim. Okay? So this is the idea. We are also considering the prestige of those who connect to you, not just uh, so kind of a recursive relationship. And this is, by the way, the main idea behind the page rank algorithm, which we'll also discuss briefly. Okay? So how do you define this? So let's say okay. So usually these links we will consider them to be direct links. मतलब डायरेक्ट लिंक का मतलब ये एक हॉप में आप लिंक कर रहे हैं. ठीक है. So in that case, then the rank prestige PR of a node I would simply be defined as, you have to take the summation for all node J that is not I. ठीक है. And then we will have the PR of that node J multiplied by basically whether that node connects to I or not. ठीक है. तो उसके लिए हम एक मैट्रिक्स डिफाइन कर लेते हैं, या एडजेंसिस एल ही ठीक है, या एल इज फाइन. एल, so we are looking at whether j connects to I, so इसका इंडेक्स ji होगा. So what is lji? So l basically is n by n matrix. ठीक है. फर्स्ट ऑफ ऑल हमारे पास n नोड से ग्राफ में n by n matrix है. So l ij is equal to 1 if I connects to j and 0 other y. ठीक है. So it's a binary matrix 1 or 0. And by the way, this is also the adjacency matrix. of the graph. ठीक है, एडजेंसी मैट्रिक्स भी इस तरह ही होता है. सो एसेंशियली जो nodes उसको connect कर रहे हैं, we simply add their prestiges and this would give the prestige of the node I. So as you can see, this is a recursive relationship. तो इसको हमने मैट्रिक्स फॉर्म में लिख सकते हैं. लेट्स से आई मैट्रिक्स फॉर्म में मैं रैंक प्रेस्टीज को सिंपली पी कह रहा हूँ. लेट्स से दिस इज रैंक प्रेस्टीज वेक्टर. ठीक है, पी. सो एल मेरे पास वही एडजेंसी मैट्रिक्स है. So I can now write this as L, sorry, I can write this as P is equal to L transpose of P again. ठीक है. So P appears on both sides of this equation. So you are familiar with this equation, eigen equation of an eigen system. So ये हम डिटेल में बाद में डिस्कस करेंगे when we talk about the page rank algorithm. But we need to solve this equation, set of equations, because there are n equations in this. And solution, of course, will come from the solution of the eigen system problem. So this is the rank prestige. And the rank prestige of a node in a network depends on the prestiges of other nodes to which that links to it. Okay, uh, so I'm going in a measured pace, not very fast, I guess. Uh, okay, so now let's move on to two other concepts of, of a graph that can define the similarity of two nodes. And we have actually talked about a very similar concept in the previous lecture, the shared nearest neighbor. But वही concept हम with an example of biblometrics हम discuss करेंगे. Although it has applications in others, but bibliometrics की application is easy to understand. So one is called the co-citation index. ठीक है. So what is the idea here? Again, now we have nodes are research papers. ठीक है. So nodes are research papers. An edge exists between I and J if I cites J. So do you understand this? Nodes are research papers. Research papers आपने देखे होंगे. Research paper references होते हैं. So let's me talk about research paper I. अब research paper I has references at the end. और references में कोई और paper J है. So I citing another paper J. So that means that I would have a edge to the paper J. If I cites another paper K, it will also have edge to paper K. ठीक है. ठीक है. So I and J would be similar. By the way, this is the case for co-citation. एक और जो है वो इसका inverse है. Would be similar if many papers K cite both I and J. So now we are talking about two papers I and J, or two nodes in a graph I and J, and a third node K. If the third node K is connected to both I and J, and there are many such K nodes, that means that I and J are very similar. ठीक है. So again, we will use that matrix that we defined earlier. So let Lij is equal to 1 means that I sides j, ठीक है, and Lij is equal to 0 otherwise, ठीक है. Lij का मतलब क्या है कि if I has a reference to paper j, then this Lij would be 1, otherwise would be 0. So if we have this matrix, then we can define the similarity or the co-citation index C between I and j as sum over k for L ki multiplied by L kj, ठीक है. So for all k, for k not equal to I and j, of course, ठीक है. What do you understand from this? Lki, if k refers to I, this would be 1. If k also refers to j, this also would be 1. So together ये 1 हो जाएगा, तो ये सारों का sum हो जाएगा, ठीक है. But if any of this is not 1, 0 है, let's say ki 0 है, तो ये product 0 हो जाएगा, तो ये count नहीं होगा. So in other words, this question is counting the number of k's that link to both I and j. ठीक है. So of course, this is again a similarity and this is absolute number. This is numbers को normalize करना चाहें तो normalize आप कर सकते हैं. What is the maximum number of nodes in the network, उससे divide कर लें या n-2 से कर लें, because I and j तो आपने consider किया हुआ है. So normalized by dividing by n, or if you want to be more precise, by n-2. ठीक है. And the other measure, which is a complement of this, the mirror of this, is called the this one was called the co-citation index. That is, the other one is called biblometric coupling. Okay? That is actually the reverse of that. So what does that says? I and j would be similar if both cite many papers k. पहले था कि k कोई था वो साइट आई एन जे को कर रहा है. अब हम देख रहे हैं कि आई एन जे में दोनों एक ही पेपर साइट कर रहे हैं, इसका मतलब आई एन जे सिमिलर होंगे. So the example here, of course, is from bibliometrics, but as I said, this applies to other networks as well, social networks maybe, computer networks maybe, and so on. So a popular, of course, हुआ था from bibliometrics, so that's why we are using that terminology. तो इसमें फिर of course जो bibliometric index होगा for I and j is now again a similar equation, sum for all k, but now these equations would be slightly different. L, अब हम देख रहे हैं कि I sides k and also j sides k. ठीक है. So this will now count all those k's that are cited by both I and j. And again आपने normalize करना तब divide by n कर सकते हैं या n-2. So you can, by the way, ये जो अभी हमने last में ये coupling है, ये this is very similar to the shared nearest neighbor that we talked about earlier. Of course, in shared nearest neighbor, we took k as a parameter. सो हेयर के पैरामीटर नहीं है, यहाँ ऑल कनेक्टिविटीज हैं। ठीक है, वहाँ के नियरेस्ट नेबर हम लेते थे सिर्फ, एंड देन जो कॉमन नेबर्स थे वो सिमिलैरिटी बना रही थी। यहाँ भी ये कॉमन नेबर्स हैं, आई साइड से पेपर के, जे साइड से पेपर के, so all of those that are cited will be common to both I and J. ठीक है, so this is very similar to that. अच्छा, तो next we will briefly talk about the page rank algorithm. I won't go into the detail of that. वो probably next class में शुरू होगा, and then we'll briefly talk about some ways of detecting communities in graphs. So communities would be highly connected subgraphs. ठीक है, and they have applications, as I said, in detecting groups of people that have the same interest and so on. So ये part I think I'll cover in the next class, and so that would, I think, probably bring us towards the end of the semester. We don't wouldn't have much more time to cover any new topic. एक आपका of course guest lecture भी है, वो ईद के बाद हम रखेंगे। एक इंडस्ट्री से हमारे ही ग्रेजुएट हैं, he has worked in a number of companies in the data science domain in Pakistan. वो आपको फिर बताएंगे अपना एक्सपीरियंसेस। ठीक है, एनी क्वेश्चंस? एनी क्वेश्चंस? Right, no questions, so that we can then end this session. We'll meet again inshallah on Tuesday, and that's I think all from my side.